Hello, my wonderful AP Chemistry chickadees. Hopefully gas laws are starting to kind of come together for you, combined with if you combine the simulation you did plus the notes from the first day, hopefully things are going to be making a little bit more sense to you. We are going to be talking today about pressure and volume and temperature and how those three things are related when we talk about gases, and more importantly, the math that we use when we're talking about those three things. We aren't going to be getting into moles of gas just quite yet. Trust me, that's coming and you're going to love it. But we are going to be talking about pressure, volume, and temperature relationships. The equation that I'll show you kind of at the end of this slideshow is going to be on your equation sheet for the AP exam. So that should be hopefully helpful for you. But like I said, we're going to talk about kind of each of them as duos, and then we'll do a remix kind of them and put them all together at the end. So the first relationship we're going to talk about is the pressure versus volume relationship, which is technically called Boyle's law. Now, you don't need to know the names of the laws. You just need to know how they work. And the general way that it works is that if I have a gas and I take that gas, and by the way, temperature is constant in this situation. So if I take that gas and I compress the container down in size, I am going to increase the pressure of that gas. And if I take a container and I expand the size while changing nothing about the temp or the amount of gas inside, I'm going to make the pressure lower. So as V goes down, the P goes up, and vice versa. As V goes up, P goes down. And the reason for that is because if I have the same number of particles stuck in a container, remember, pressure is caused by the number of collisions with the side of the container. If I have the same number of gas particles in a smaller amount of volume, they're going to hit the sides of the container more, which is going to increase the pressure. Now, gases do actually hit a point where if you apply enough pressure, you can actually make them stick together and turn them into a liquid. But generally, it takes a lot of pressure to make that happen. I have a demo it's a video of a demo that I think is a good one. So I'm going to have that one come up next, and hopefully it works. So the setup of this is that this little kind of jar that you're seeing here is what we call a vacuum chamber. And what they do is they hook it up to a pump that pulls the air out of this. And this is shaving cream that is in that vacuum chamber. Now, shaving cream is a mixture of the cream itself plus a little bit of air mixed into that. And again, remember, the relationship is that if P goes down, V goes up, and if P goes up, V goes down. So let's take a look and see what happens. What they're doing is they're going to be pumping the air out. Make a prediction what you think is going to happen. So you can see they've kind of tightened the vacuum pump up, and here's what we're getting. So you can see this rapid expansion of this foam inside of there. And that's because the gas particles that are trapped in the foam, if they have a lower pressure around them, they can expand, and they have the volume that really grows really quickly with that. And you will see that a lot with gases, is that if there's a lower pressure environment, it will expand to fit the size of its container. Now, Boyle's law mathematically is P1 times V1 equals P2 times V2. And that's because the moles of gas are constant. So it's kind of like our M1 V1 thing, the same idea here. So P1 and V1 equals P2 and V2. And what would happen in a Boyle's law problem is that you would have three of these values, and you'd need to solve for the other one using algebra. Okay. The second relationship that we're going to be talking about is the volume versus temperature relationship, which is Charles' law. So in this case, and this is kind of a weird one to think about, the pressure needs to remain constant. So the total number of collisions with the side of the container needs to stay the same. Also, what stays the same is the number of moles. So again, amount of gas isn't changing in here. So what happens is, if you think about the volume versus temperature relationship, if I take a gas and I heat it up, it is going to move faster. And when it moves faster, two things are going to happen. One, they are going to hit the sides of the container more. And two, they're going to hit the sides of the container with a higher force. Both of those things would, in theory, if you couldn't move your container, they would make the pressure go up. But we want the pressure to stay the same. So what has to happen is, to compensate for that, the container needs to expand so that you have more volume so that the collision numbers go down. And so what happens is if I have the temperature of my container go down, my volume of my container is going to go down to maintain that pressure. If I have temp go up, my volume is going to go up to maintain that as well. And I've got another demo here. I'm going to show you this cool guy here. What he's going to be doing is he's going to be taking liquid nitrogen and pouring it over a balloon. So obviously the temperature is going to go down. See if you can kind of predict what's going to happen here. So he's got that flask of liquid nitrogen on the balloon. And you can see as he pours that on there that the volume is shrinking. So that balloon is that flexible container we talked about. And as you do that, the particles slow down. And when they slow down, they don't apply as much pressure. Now, as the liquid nitrogen kind of evaporates, you'll see the temperature go up. You can see that gas escaping there. And now you have your volume going up again because the temperature is going up. So that's that temperature and volume relationship. Now, Charles' law looks a little bit different than Boyle's law. Boyle's law was as one goes up, the other goes down. With this, one goes up, the other goes up. So with this relationship, volume 1 over temperature 1 equals volume 2 over temperature 2. And with these calculations, like I said before, gas law problems need to be solved with Kelvin temperatures because you can't have a negative temp in gas law calculations. What that means is if you have a Celsius temperature, you're going to always want to add 273. You might see it be 273.15, and that's fine too. Both of them are acceptable on the exam. So you got to add those numbers to make them Kelvin temperatures. If you do this without Kelvin, you will get them wrong. So please make sure that you do this. Algebra's just a little hairier here because you might have to like solve for T2, and then you just got to be very careful with your variables. Okay. The last one is the pressure versus temperature law, which is considered Gay-Lussac's law. And the way that it works is that if we have a fixed volume container in this situation, and the number of moles are the same as well, if I take a gas and I heat it up, we know that the container is going to not change volume, but the particles inside are going to hit the sides of the container more and hit them with more force. When that happens, the pressure goes up. So the relationship is T goes up, P goes up. T goes down, P goes down. And the example I have for you is actually kind of a crazy situation. Now, they're going to explain it, but to start off, this is a fire at a welding supply company. And welding supplies, what they do is they have gases that are bottled under very high pressure situations. And they are fixed containers. So they're these really heavy duty metal containers. And I think the audio is going to be on here, so we'll listen up.
Dallas, Texas. A welding supply company minutes from downtown is on fire. The business stores hundreds of welding tanks filled with acetylene, a highly flammable gas. The intense heat of the fire is causing pressure to rise inside the 130-pound tanks, and they could explode at any moment. This precarious situation has forced an evacuation of the area and emergency crews to stand back. The building is engulfed in flames, and the volatile canisters can't sustain the burning temperature for long. Police have shut down one side of the freeway, but the other side remains open.
As a side note, this is very bad.
If these tanks burst, they could turn into lethal projectiles. This situation, combined with being a stone's throw from downtown Dallas, has all the ingredients for what could become a major disaster. Then, the first tank explodes and flies across buildings.
Okay. So what you're seeing there is, let me see if I can go back to that video.
Dallas, Texas. A welding supply company minutes a truck on the far side of the freeway.
So what you're seeing here, all these containers that are exploding are high-pressured containers that are heated up.
A slew of flaming projectiles vault hundreds of feet into the air. They pummel the freeway, at times barely missing drivers. The building is now a launch center for the acetylene tanks and is completely out of control.
Okay, obviously not a good scenario. So in that situation, and anytime you have a high pressure or a sealed container under that heat, what happens is the particles get hotter, they move faster, they hit harder, they hit more frequently, and they increase the pressure. And eventually you will get a container failure. That's real bad. So you can see here, nobody got hurt, shockingly, in that situation. Like the canisters kind of flying all over the place, but it's always kind of my favorite video because it is the most extreme application of Gay-Lussac's law. Maybe I shouldn't be so excited about this, but it's crazy. Okay. Oh, we don't need to go.
Texas. A welding supply
Oh,
company
no.
minutes from downtown is on.
It's falling apart here. Okay. So this is Gay-Lussac's law mathematically. Because they're related directly, as one goes up, the other goes up. The law looks a lot like Charles' law. P1 over T1 equals P2 over T2. Okay. So here's the deal. They don't have all three of these printed on your test. What they do is they actually have something called the combined gas law. So what the combined gas law does is it takes all of those laws and it combines them. So it is P1 times V1 over T1 equals P2 times V2 over T2. And here's how I like to solve these problems. The trick with these is that you've got to read the problem carefully and figure out what variables you have changing and what variables you don't have changing. Then what you do is the variables that don't change, you cover up in the law. So if I'm doing a problem and there is no mention of temperature, I cover up the T part of my law, like literally physically cover it up. And then my law is P1 times V1 equals P2 times V2. If my container is a fixed volume, I cover up the V's. And then I have P1 over T1 equals P2 over T2. So you're going to use this law, but then kind of use it and wipe out the things that aren't changing. And that will help you figure things out. Like I said, when the amount of gas changes, that's a whole different ball of wax. But if we just have a container of gas that's expanding or contracting or doing something, then we use the combined gas law. There are 3 examples that I'm going to go over in the next video. I think it would be wise for you to try them. So I'm going to give you them to take a look at. And I think it'd be smart of you to try them without me and then take a look at the video so we can work over them. Okay, so the first example is a gas sample is held at constant pressure. Gas occupies 3.62 liters of volume when the temperature is 21.6 degrees Celsius. Remember, temperatures have to be in Kelvin. The sample was cooled and decreased in size to 3.45 liters. Determine the temperature the sample must be at when the volume is 3.45 liters. So that's the first one. Second example, ooh, it's got pictures. Okay, so you've got this syringe that starts at 4 milliliters. The pressure of the gas in the syringe is decreased to 1/2 its original pressure. So this is my first syringe. Temperature stays the same. Which syringe best represents the syringe after the change? And you've got to pick A, B, C, or D. Okay. And the last one, example 3, a 6.35 liter sample of carbon monoxide is collected at 55 degrees Celsius and 0.892 atmospheres. What volume will the gas occupy at 1.05 atmospheres and 20 degrees Celsius? So I would take a pause, give these 3 problems a try, and then come on back to my next video and we will go over them. If you have any questions, just shoot me a message. And if not, good luck.